So I think we should begin now. As I said, today's session is going to be small molecule accurate mass analysis. Can I just remind everyone, the session is being recorded. Please stay mute and there will be an opportunity to ask questions at the end. So what we're going to cover today is what we actually mean by accurate mass. Mass spectrometry is kind of a branch of physics, and like anything in physics, the more you look at it, what appears to be simple turns out to be rather more complicated. We'll look at different types of accurate mass instruments, how we calculate monoisotopic mass, which is the measurement that will be of interest to chemists. We'll look at different types of calibration on the instruments. We'll look at mass defect, adducts and multimers, how we determine charge state for a small molecule, how we will use accurate mass to determine molecular composition, what we can do with isotope matching, and then finally I will give you some advice about how to handle small molecules. Okay, so accurate mass, what do we mean by accurate mass? So basically this is a mass measurement better than 5 ppm, that's 5 parts per million. If we take a typical small molecule of around 300 Daltons, that computes to a mass accuracy better than 0.0015 Daltons. I would say you need to, when quoting accurate mass, you need to do that to 4 decimal places. And that should be sufficient to establish the molecular composition if you can get the mass measurement better than 5 ppm. I've listed some instrument types here. You'll notice that most of them can measure to 5 ppm or better. So FTICR is the best, closely followed by Orbitrap. Magnetic sector instruments, you will probably not come across those very frequently, but also TOF, QTOF and triple quad instruments are all accurate mass. The only one that isn't is an ion trap. I'm going to spend quite a lot of time on some mass definitions. I wouldn't take this as read. It's important that we understand exactly what we're talking about. As I said in the preamble, precision in small molecule analysis is absolutely crucial. So we start by defining atomic weight. So 1 Dalton, as I'm sure everybody knows, this is 1/12 of the mass of a neutral carbon atom. And here's an excerpt from the periodic table, and you can see here we have actually the mass of carbon listed as a range because carbon has more than one isotope. It's roughly 1% carbon-13, and the abundance of those isotopes is the geographical abundance of those isotopes is represented in this figure. So the measurement that most people are familiar with is molecular mass or molecular weight. So this is the sum of the atomic weights for each constituent element in your compound. And so it's derived from the molecular formula. And the atomic weight or the molecular mass, this is what you would measure out in the laboratory when you're weighing out your chemicals. And this is what is quoted on the label on any bottle of chemicals. Nominal mass, so this is the mass of a molecule calculated using the most abundant isotope for each element, and then it's rounded to the nearest integer. And you'll see what that is a useful value, and you'll see what that's for in a moment. The accurate mass, so accurate mass is the experimentally determined mass. So when we measure the mass of an ion in the mass spectrometer, if it's an accurate mass instrument, this would be the accurate mass of that compound. The exact mass, so this is the calculated mass from when you know the isotopic composition and you know the elemental formula, and the exact mass is the theoretical mass. So obviously that may be slightly different from the accurate mass that you've measured. Monoisotopic mass, so this is the exact mass from the principal isotope. So for a typical carbon compound, it would be the lightest isotope. So it's the first isotope in your isotope series. But that's not necessarily the case. For some atoms, for example, iron or argon, the principal isotope is not necessarily the lightest. Also, monoisotopic mass, we cannot use this universally. It's very useful for small molecules, but as the mass of your compound increases, very often you will not observe the monoisotopic mass. But you can still derive it from the isotopic distribution. Mass defect. So this is the difference between the exact mass and the nearest integer mass. So this is the nominal mass. And the mass defect is a useful measure. I've indicated the mass defect is indicated here. This is a mass calculator. We put in the formula. It calculates various values for the mass, but it also shows you the mass defect. So the mass defect arises because of the way a Dalton is defined. And if we have a positive mass defect, that indicates that we will have in our compound, if it's a hydrocarbon, we will have a preponderance of hydrogen and also nitrogen. If the mass defect is negative, which is less common, then there is a preponderance of these elements: oxygen, sulfur, phosphorus, and halogens. Carbon itself, because of the way it's defined, it has a zero mass defect. There's also an interesting thing that you can use from the nominal mass is organic compounds which contain these elements. They're either going to have an odd or an even nominal mass. If the nominal mass is odd, then that means there is an odd number of nitrogens. If the nominal mass is even, then that means there is an even number of nitrogens. So you can use the nitrogen rule to help you determine the composition of an unknown compound. So we're still looking at mass definitions, but I just want to reinforce this. If we take a typical carbon compound, here's one. It has 26 carbon atoms. When we measure it in the mass spectrometer, we don't see a single peak, as you will realize. We see an isotope envelope. And in this particular one, there are 4 visible isotope peaks. And because the incidence of carbon-13 is 1 in 100, is 1%. In this mass, so note that we don't see the monoisotopic mass. We will see the mass of the ion. So this is MH plus. So this is 1 atomic mass unit heavier than our monoisotopic mass. And this arises because we have 26 carbon atoms and all of them are carbon-12. In this peak represents the same compound where there are 25 atoms of carbon-12 and 1 atom of carbon-13. This peak, obviously 24 carbon-12 and 2 carbon-13s, and so on. So this is the monoisotopic mass for this compound, and as you can see, this is the protonated mass. We don't use the average mass because, as you can see, we can't actually measure it. There is nothing there to measure at the average mass for a small molecule. This is the nominal mass, 429. And in this case, the monoisotopic mass is also the most abundant mass, but that is not necessarily the case. That holds for small molecules, but once you get over about a mass of about 1,000 Daltons, then the most abundant mass is not going to be the monoisotopic mass. So just to illustrate this a little further, I've shown you spectra here for two different compounds. So caffeine is a very small molecule, nominal mass of 194, and labeled on here is the nominal mass in blue, the monoisotopic mass, which corresponds to the peak, in purple, and the average mass in green. If you're going to use accurate mass to identify this compound, obviously you would want to get a match to the monoisotopic mass. But the differences between these is relatively small. But that's not the case as we go up the mass scale. So when you now look at glucagon in the lower spectrum, you can see that obviously the nominal mass we don't measure. Here's the monoisotopic mass on the first isotope, but it's not the most abundant. The most abundant mass is this one, and the average mass is here. But you'll see that there is still a substantial difference between the average mass, the most abundant mass, and the monoisotopic mass. So some guidelines for when you are using accurate mass: always perform the mass calculation yourself. Do not trust anyone else to do this. Use the molecular formula. There are mass calculators available, and calculate the monoisotopic mass yourself, so you know you're working with the right one. In your spectrum, you're either going to look for the protonated mass or the deprotonated mass if you're working with negative ion. Depending on what you're working on, if you're working on small molecules, you should always use the monoisotopic mass. However, if you're working on biopolymers, so you're working on proteins, on nucleic acids, or anything large, you should not use the monoisotopic mass because you will not be able to measure it. You will use the average mass. Okay, that's all I want to say about masses. Let's talk now about how we calibrate the instrument. So it goes without saying, you should always perform a calibration. It should be an external calibration, and I would advise that you always do that before doing accurate mass work. These instruments are very accurate, but only if they've been calibrated. And you want to know that that calibration is going to be valid for the measurement you're going to take. It doesn't take very long. The instruments we have can be calibrated in about less than 5 minutes. You do need to calibrate the instrument. If you change some of the parameters of the instrument, you will need to recalibrate it. So in our instrument, we work at different mass ranges. When we switch those mass ranges, we need to recalibrate. It's particularly important in negative ion mode. We don't use it in negative ion mode very often, but when you do, you must make sure it's been calibrated in that mode. So on our instrument, this is an Agilent 6530 QTOF. It's an extremely accurate machine. The mass stability is excellent. And when we are calibrating, we would expect an accuracy of 1 part per million or less. If you're using that instrument, the mass spec staff will train you in how to do this. I would just say calibration and tuning, they are different processes. So calibration is basically making sure that the instrument is matching the measured masses to its internal list of calibrants, which is here. Tuning is slightly different. Tuning is basically optimizing the transmission of ions through the mass spectrometer in order to get the highest sensitivity and the sharpest resolution. In practice, you need high sensitivity and highest resolution in order to get the optimal calibration. So very often these two processes are combined. And this is what it looks like on our QTOF instrument. So these are the mass calibrants. We're calibrating across the mass range from 50 Daltons up to 3,200. These are the masses of our external calibrants, and they're quoted to 5 decimal places. And here they are being measured to 4 decimal places. And all the instrument is doing is basically matching those to the theoretical masses, and then adjusting the TOF, the time of flight, to match those masses. So that's external calibration. So external calibration is absolutely fine, but you may have calibrated instrument, and then you may be making measurements for the next hour or two, and over that time the calibration may drift. How much depends on the instrument. On our instrument there just isn't very much, but in order to correct for that, you can constantly recalibrate the instrument using an internal calibrant. And on the 6530 QTOF, this is a dual spray instrument. What that means is there is a nebulizer here. This is where your sample is introduced. There is a second nebulizer here, and this is where your internal calibrant can be introduced. So you spray, you can choose a calibrant. It's usually one of the external calibrants. In this case, the one chosen is mass 1221, and that is sprayed continuously at a very low level at the same time as you're doing your experiment, and there is a continuous internal correction based on that mass. We don't generally use that. We do use it sometimes, but it's not that common because our instrument, the mass stability, is very, very good. That can't be said for all mass spectrometers. In my own experience, I know Waters instruments, that's not the case. So on a Waters instrument, you must always use the internal calibration. In Waters instruments, they refer to this as lock spray, and there's a baffle here. So what happens is when you're running your sample, this baffle is continually switching. I think it switches about once every 15 seconds and introduces spray from the second nebulizer, which is your lock spray, and you can have this continuous mass calibration. So when you are analyzing your spectrum, what you are going to be looking for in your spectrum, of course, you're not going to see the neutral mass because we can't measure neutrals. You are going to be seeing either the protonated mass if we're in positive ion mode, or you'd be looking for the deprotonated mass if we're in negative ion mode. You may not see either of those. You may see the sodiated mass. Okay, so keep that in mind. The mass may well be 22 Daltons heavier than your theoretical mass. It's 22 rather than 23 because you are the sodium adduct is loss of a proton and addition of a sodium ion. You can also see this. So this is a dimer. So it's a singly sodiated dimer ion. You can see variations in that. You may also see potassium ions. This is for small molecule. If you are working on anything larger than about 600 Daltons, you should use an ion table. Use the ion table to determine the mass to charge, and then you're going to look for multiple charge states. So just to show you, this is a mass calculator. So you put in your base formula here, and these are the species where it calculates the ions that you may see. In negative ion mode, there's a different set of ions you may be looking for. You may need to identify the charge state. So if you're familiar with working with proteins, we would have multiple charge states and we will deconvolute those charges. You don't generally need to do that with small molecules because the spectra are simpler, there are fewer charge states, but you can still have multiple charge states. And they're quite easy to work with. So if you take this compound, this is a mass of 591, and this is the isotope envelope. And if we measure the mass between the different isotopes, this corresponds to 1 atomic mass unit. And what that tells us is this ion is singly charged. If we now take the doubly charged version of this ion and measure the mass between the separation between the isotopes, it's 0.5 atomic mass units. So that means this must be a doubly charged ion. If it's 0.33, it will be a triply charged ion, and so on. So it's very simple to identify. So we've measured the accurate mass, and we can use this to determine the elemental composition. So in our software, there is a formula calculator. So what we do with this is we can give it an accurate mass that we've measured and set some defined parameters, for example, which elements we are expecting and the maximum and minimum number of each of these elements. So you can program this into here. And for a given mass at a given accuracy within these defined parameters, there can be a single molecular formula which fits that mass. So you can, from this mass here, you can derive that this is the only carbon compound that will have that formula. And that works for small molecules. But obviously, the more elements you have in your, the more constituent elements you have in your compound, the more possibilities there will be. So when you try this with a larger mass, you'll see that actually there are quite a few molecular formulas that fit that mass within the tolerance that you've chosen. So it's less useful for large compounds, but for small molecules, it can work quite well. Another tool that you have are isotopes. So we've looked at some of the isotopes of carbon. So carbon has, the principal isotope is carbon-12 and 1% carbon-13. But if you're a chemist, you'll probably be familiar with the idea that isotopes can have different abundances, and they can be characteristic. So if you take, for example, bromine here, 50% is 79, 50% is 81, and there is none at mass 80. And these two almost equal isotopes, 2 Daltons apart, this is characteristic of bromine. This isotope envelope here is characteristic for chlorine, and there's another one here characteristic for iron. So some elements will have unusual characteristic isotope distributions, as I've shown you, and we can use an isotope distribution calculator to generate an isotope fingerprint, and I'll give an example of that. So here's some work we did several years ago on a protein called ISPD, and it purifies yellow. It's not clear, but when the protein is denatured, that color is lost. So the assumption that we had was it must be a chromophore. We did denaturing LCMS, and we had a compound here at 616, and we knew that that was the mass of free heme, but we couldn't measure that mass to within the desired accuracy. We could only get the mass accurate to about 17 parts per million, and the reason for that is one of our calibrants unfortunately lands pretty much on top of this mass. It's 622, so we couldn't get that mass particularly accurate. However, what we can do is we can use isotope matching. And so what we did is we took the composition of heme, and we put this into an isotope, theoretical isotope calculator, and this is the theoretical isotope pattern for heme, including the iron. And it's quite unusual. As you can see, you've got these peaks here, which you would not expect with a normal carbon-containing compound without iron. And this is the isotope envelope that we measured. And from this, so all these peaks are represented. This one is here, this one is here, and these correspond exactly to the theoretical isotope distribution. So you don't get much chance to use this, but when you do, it works extremely well. Another tool within your armory for working out what things are is fragmentation. We can do MSMS fragmentation, so this is isolating your compound via its mass to charge, and then doing a single round of fragmentation, which would be MS, or you can isolate a fragment and fragment that again, and you can do multiple rounds of fragmentation, and you can use this to infer the structure. So you can do this a priori. If you're a skilled chemist, you're able to do this. You can also use the fragmentation prediction software. There are software packages out there which you can use, or you can take your fragment, which has been fragmented under standard conditions, and then there are small molecule fragmentation libraries which you can try and match your spectrum to. Another tool that you have is the extracted ion chromatogram. So some of you will be familiar with total ion chromatogram. This is this trace at the top. So here we're measuring, this is the total ion current versus the time in your chromatogram. This is about 12 minutes. So when you have a peak in your total ion chromatogram, then there is something eluting into the mass spectrometer, but you don't necessarily know what it is. This is a base peak chromatogram. Very often it's similar. In your base peak chromatogram, this is the mass of the most abundant ion in your spectrum, plotted against time. But extracted ion chromatogram is where you've selected a particular MZ of interest. In this case, the MZ of interest is 591.3 daltons, and that is the mass of OGNG, which is the detergent, and that will give you a peak which corresponds only to that MZ value. It's actually not OGNG, it's sodiated OGNG. OGNG itself is 568 daltons. Alongside that, or beneath that, we have another extracted ion chromatogram, which is 1157. So this is the OGNG dimer, which is also sodiated. So you can use extracted ion chromatograms to help you identify a compound of interest, because your singly charged ion, your doubly charged ion, and your triply charged ion, they will have different MZ value, but they are chemically the same thing, which means that they will behave exactly the same way on LC. So in your chromatogram, they will elute at the same time. And so this is a way of helping you identify that this is actually the species you're interested in. So I wouldn't pretend to be an expert on small molecule LC-MS, and the reason for that is most of the work we do is on biopolymers, and they are fairly predictable. So peptides and proteins, nucleic acids, will all behave generally similarly in LC and in mass spec. Small molecules, of course, well, small molecule can be almost anything. So you have the full range of chemical space open to you. And what that means is that their behavior is not necessarily going to be predictable. The first thing you have to make sure is that your compound is going to be soluble in the mobile phase you're using. That's not necessarily going to be the case, but you need to make sure that it's soluble in your mobile phase. You can change the mobile phase if it's not. Whatever solvent you use, it must be volatile. If it's not volatile, it's not mass spec compatible. And so your compound, whatever you've dissolved your compound in, it needs to be volatile, and it also needs to be miscible with the other mobile phases you may be using. You can use DMSO. It's tolerable in the mass spec in fairly small amounts. It's not volatile, but it's not volatile under normal conditions. So you can't spray that directly, but you can dilute it to a fairly, let's say below 0.1%, and you can tolerate that in mass spectrometry. Most ion species, whether they are charged or whether they're neutral, they will ionize to some extent in positive ion. Doesn't really matter what the charge is, most species will ionize. There's one or two that will not. Very small, very electronegative species will not ionize in positive ion mode, and you will have to use negative ion mode. Most small organics, they will be retained on a C18 column. So C18 is pretty much standard for small molecule HPLC, and most organic compounds will be retained on that column and elute following somewhere in a gradient of an ascending gradient, either acetonitrile or methanol. There are occasions when compound will actually not bind to the column, and it's going to come out in the void volume if it's extremely hydrophilic. Alternatively, if it's extremely hydrophobic, it may bind to the column and it may not come off. In that case, you can use a different chemistry on your column. You can maybe use a C4 or a C3. If your compounds are insoluble, or if they elute in the void volume, or if, as I said, they bind irreversibly to the column, the way to proceed then is to use direct infusion. And you would do this with a mass spec compatible solvent. So what do I mean by direct infusion? Okay, so this is very simple. Direct infusion is basically what people used to do in the days before hyphenated mass spectrometry, before the days of LCMS. So what you are doing is you are directly introducing your compound into the mass spectrometer. So you do this using a syringe pump. You have your compound dissolved in a volatile solvent, and it can be introduced at a constant flow rate, a fairly low flow rate, directly into the mass spectrometer. So you have to do this manually. So the sample introduction is quite slow. It's quite time consuming. You have to reload the syringe and continually rinse it from sample to sample. Also, the data collection is going to be slow. You're bypassing the HPLC system here, but this can work quite well, provided your sample is salt-free. If there is salt in your sample, do not do this. And also your sample needs to be pure. So you're not getting any of the benefits of HPLC, which is desalting and separating your various components in your mixture. But if you have a pure compound, direct infusion can work quite well. So just to kind of finish up, I have come up with I describe as a decision tree for what to do with small molecules, because, as I said, they are less predictable than peptides and nucleic acids. I would always start doing a simple LCMS analysis, just diluting the sample, maybe 1 in 100 or maybe 1 in 1,000, and put 1% formic acid. If it's soluble, you can run it. You should always do a blank injection. I mean, that goes for pretty much anything in mass spec. You should always do the blank injection. It's particularly important because in the blank you will see a number of species which are characteristic of the solvent, or they can come, in some cases they can come from glassware. So you want to be able to eliminate those. We would do this on a C3 cartridge and methanol gradient. If you get your spectrum, that's great. If you don't see that, you can use the extracted ion chromatogram. You can predict mass to charge values and see if you can see that. If you're not seeing anything, you can switch the mode to negative ion and then try that. If you're compound is not soluble in the chosen solvent, you can try a different solvent. It must be mass spec compatible, but you can try direct infusion. If you're not getting anything, you could try negative ion. If you're still not getting anything, then I would move to alternative ionization methods. Okay, I would, everything will ionize by mass spec. Everything. I've never come across anything that didn't, but it's not necessarily going to work in LC conditions you've chosen or with the ionization mode you've chosen. There are a number of different ionization modes available. Unfortunately, none of these are available in our lab, but if you go to a chemistry research lab, they will have access to several of these chemical ionization methods: atmospheric pressure, chemical ionization, fast atom bombardment, they're moldy. There are a range of different ionization methods available to you if electrospray is not working. But I would say that electrospray is pretty good. Most things should ionize in electrospray. Okay, so that's all I really want to say. Just to summarize, we've looked at different accurate mass instruments. So these are triple quad, a time of flight instrument, Orbitrap, and FTICR. And by accurate mass, we mean mass accuracy of less than 5 parts per million. I hope now you understand what monoisotopic mass means, and that you understand you need to calculate this yourself from the molecular formula. You always need to calibrate your instrument before you start work. Always perform a pre-run blank. When you're analyzing your spectrum, you're going to be looking for adducts, so typically sodium adducts. You can be looking for multimers. There may be multimers. You may also expect multiple charge states, so we've seen how to spot those. I've shown you how to use your extracted ion chromatogram. And then for identifying unknowns, we can use a number of tools. We can use the mass defect. We can use the nitrogen rule. We've got the molecular composition from the accurate mass. We have the option of using isotope matching, and we also have the option of fragmentation. So small molecule chromatography and ionization, it's not necessarily predictable because all small molecules are different. You need to pay particular attention to the solubility of your compound and also its charge. And as I've said, direct infusion, this can work quite well with any mass spec compatible solvent, provided your sample is pure. That's all I want to say about accurate mass. Just to remind you, next week we'll be talking about reverse phase HPLC. That's a key skill in mass spectrometry, and that's what we'll be talking about next week. So I'm going to stop there, and I'll be very happy to answer your questions.
Hi, Rod. I was wondering, you use the standard C3 column for small molecule analysis because you use it for the proteins as well.
Yes, we do. Yeah, the reason, that's a good question. The reason for that is because it's on the machine and it's a go-to method. People are familiar with that method. So in general, it will work. If I was developing a small molecule method from scratch, I would not use the C3. I would use the C18 because that's far more likely to trap your compound of interest. So yeah, C18, I would say that would be better for small molecule analysis than C3. But C3 is just an easy go-to start point.
Okay, thanks. And yeah, thanks.